this video I discuss how electronic currents can be calculated within single molecules. Moore's law states that the number of transistors on a microchip doubles every 2 years. However, because integrated circuits are now so small, the number of transistors which can fit on a microchip is reaching its limit. In order to continue to increase the processing power of computer chips while decreasing their size, we must build electrical components from even smaller structures. Molecular electronics does this by employing single molecules as components within the integrated circuits. In principle, this could lead to computer chips 1/10 of their current size, with equal or greater processing power. The current voltage characteristics of single molecules can now be measured experimentally. However, this is an expensive and time-consuming way to design molecular electronics. Ideally, theoretical models would be employed to determine these electrical characteristics, i.e. the change in the current induced by a change in the voltage. However, most advanced theoretical models at present rely on approximations which are insecure in the presence of strong electrical currents. Therefore, we need to develop improved approximations which reliably yield electronic currents within single molecules. The dynamics of electrons in a molecule are described by the many-body Schrödinger equation. From this equation, the electron's many-body probability density can be calculated, from which the electrical current can be obtained via the continuity equation. However, for most molecules, this equation cannot be solved, even by the world's most powerful supercomputers, because of the electron-electron interaction. In time-dependent Kohn-Sham theory, within time-dependent density functional theory, the many-body electron density can be calculated via an auxiliary system of non-interacting electrons. These non-interacting electrons feel the Kohn-Sham potential, which is defined such that the non-interacting electrons yield the interacting density. The advantage of the Kohn-Sham approach is that Kohn-Sham equations can be solved. However, part of the Kohn-Sham potential is unknown and hence must be approximated. In order to develop approximations to this unknown potential, one must study, where possible, its exact form. It turns out that the exact Kohn-Sham potential has strong dependence on the electron density everywhere in the system, meaning that no matter how far apart the electrons are, the Kohn-Sham potential in the region of one electron must know the properties of the other electrons. This makes approximating the potential difficult. Ideally, the potential we have to approximate would be concerned only with the electrons in its local vicinity. This property is known as nearsightedness. For more information on the advantage of nearsightedness in potentials, please see my published work. The Kohn-Sham approach can be generalized to allow more flexibility in the Kohn-Sham potential. Within generalized Kohn-Sham theory, the Kohn-Sham potential has two distinct parts. One part is known as the non-local potential, because in effect each electron may feel a different effective potential. The other part is known as the multiplicative or local potential, because all electrons feel the same effective potential. The standard Kohn-Sham potential consists only of the multiplicative part. Through the choice of non-local potential, one can design the corresponding multiplicative potential to be more or less nearsighted. For more information on how one achieves this, please see this paper. In this video, I will give two examples, one in which the non-local potential has been chosen such that the corresponding multiplicative potential is predominantly nearsighted. The other non-local potential is similar to the first, but it results in a multiplicative potential which is not nearsighted. The key difference between these two non-local potentials is that the first results in a different effective potential for every electron in the system, whereas the second is only different for every pair of electrons. This difference has a profound effect on the multiplicative potential, as we shall see. In both cases, we develop an approximation to the multiplicative potential on the basis of the local density only. We shall test our local density approximation to the nearsighted and to the not nearsighted multiplicative potentials by modeling simple molecules. We choose to model the hydrogen molecule in its ground state and induce a current in the molecule by applying an electric field. We model one-dimensional systems which consist of two electrons so that the exact many-body electron density, and hence the exact many-body electronic current, can be calculated, against which we can directly compare our approximate methods. Our first system is a hydrogen molecule in which the atoms have been pulled apart. This system is notoriously difficult to model with approximate methods. We then apply an electric field which causes the electron density to move. First, we compare the exact electron current to our approximate method, in which the multiplicative potential is not nearsighted. Clearly, this method does not yield an accurate current, demonstrating how ineffective a local density approximation to the potential, which is not nearsighted, is. Next, we look at the exact same system, but now the unknown potential is nearsighted. Now clearly the electron current is far more accurate. This can be seen more easily by comparing the two approximate methods directly. Therefore, we see that a simple local density approximation can be effective at yielding accurate currents, but only when the unknown potential is nearsighted. Do we see the same level of accuracy from our nearsighted approach when we model the hydrogen molecule at its natural bonding length? As before, we model this system exactly by solving the many-body time-dependent Schrödinger equation. Here we compare the nearsighted method to the exact case and see that the local density approximation remains a reliable approximation to this nearsighted potential. In conclusion, commonly used approximations within time-dependent density functional theory are unreliable for modeling strong electrical currents in molecules. We have shown that generalized Kohn-Sham theory can be used to design the unknown portion of the Kohn-Sham potential to be nearsighted, meaning that each part of the potential is primarily concerned only with the properties of the electrons in its local vicinity. Hence, a simple local density approximation to our nearsighted potential yields accurate electronic currents for prototype systems in which the approximate results can be compared against the exact.